right, so we have this idea of what's called a polyprotic acid, polyprotic bases. And so what is a polyprotic? Well, it's something that's going to be able to donate more than one H. So if we have, let's say, for example, HCl. HCl, like I have below there, this is obviously monoprotic. Okay? This is monoprotic. You could have, for example, HC2H3O2. This guy also is monoprotic. This is vinegar, acetic acid. It's got other H's there, but those aren't weakened to a point where they can be released. This might be written as this CH3COOH. That's another sort of organic way of writing vinegar. And this is the H that it will lose. Both of those monoprotic. Diprotic would be like H2SO3 or H2SO4 or H2CO3. This one happens to be a strong acid, but all the other ones are weak, and these are called diprotic. Okay? And of course, diprotic could also be referred to as polyprotic. There is triprotic, like H3PO4, which is phosphoric acid and is one of the most commonly eaten acids. It's in food as a preservation mechanism. Okay, so the number of H's that you can donate, sometimes that's pretty easy to see. This is what we call triprotic. After it loses an H, it becomes H2PO4 minus 1. This guy here actually has another term we might call amphiprotic, like amphibian. But this is a substance that can either go back, gain H, or could lose an H. Could go either way. So it's polyprotic, diprotic, and amphiprotic. It's a small little detail. Alright, so let's look at this scene here. We got which of these guys could neutralize the most base? We got a strong 0.1 molar HCl solution and two weaks. One's diprotic, one's monoprotic. And the answer is, which one can neutralize the most base? Well, really, at 1H, can neutralize one hydroxide. Whether it's in the form of just straight H or HX as in a weak acid, it doesn't matter. So in this case, which one can neutralize the most base? It's going to be phosphoric acid. It can actually neutralize 3 times as much base as the HCl can. It's got 3 times the H's. This stuff is pretty heavily in sodas, and sometimes is kind of thought to be bad for your teeth. If you were to drop a tooth into a little glass of Coca-Cola, then by the morning it's going to be gone. But, obviously people drink plenty of soda, and I don't see people's teeth completely rotting out of their mouth. So as long as you don't gargle it, and leave out your teeth for a long time, and sometimes, dentists would be a little more sensitive to how you drink soda. But eventually, when you get old, it'll be around. Alright, so how would you model a polyprotic acid? Okay, like how would I describe it? Well, let's say, for example, sulfurous acid. This acid has the ability to donate 2 H's. So how would I describe that using chemical reactions? Okay, well what I would do is I'd say, okay, well H2SO4, SO3, plus water. This is the reaction that's going to go through to produce H plus ions. HSO4 minus 1, and then H3O plus ions. This thing has a Ka value equaling 1.7 e to the negative second. Okay. All right. In this situation, what's next? Well, okay. Well, what about about this guy then? It's an acid too. So let's the next reaction. HSO, I don't know why I put 3 there because I'm so used to that, but HSO3 minus 1 plus H2O yields H3O plus SO3 minus 2. This guy has a Ka value equaling 6.4 e to the negative 8th. Now, what does this mean, these Ka values? And how would that mean for us in the beaker? I like to look at this guy as negative 2 as being like 1 out of 100. Okay? And this thing is fairly strong. I mean, as far as other acids are concerned. So this guy here would mean like if you had 100 of these, I'm just really estimating to a very small amount, minimal accuracy. But what this means is that if I have 100 of these, I get 1 of these and 1 of these. Does that make sense? That Ka value is a ratio of products over reactants, so it's like 1/100th is kind of what we have here. That would be E negative second. To put it in a visual sense. Then, of these guys that we get, okay, how many of these do we get? Well, if this is 1 of 100, this is like 1 out of almost billion. Which means if you had like about 1 billion of these things, which, you know, and I'm not doing a good job of estimating. I'm not caring of that I'm close estimating. This is a generalized idea. Again, it wouldn't be hard to have 1 billion of these things. Even if it's only 1 to 100, right? I mean, you got a lot of these things. They're very small and they're very numerous. So we would have a decent amount of these. But if you have that means I'd have to have 1 billion of these just to have 1 of these. So these guys are not very common in this solution. All right, so one thing I want to point out to you is this, is that successive Ka, like the next H, is always less common. Meaning my Ka value always gets significantly smaller. It's 1,000,000 times smaller. That's not unusual. That's the rule. I mean, it's always going to get like that. So, like on the phosphoric acid, if you looked at a beaker of phosphoric acid, how much of this versus HPO4 minus 2 versus PO4 minus 3? How would you describe the numerous amounts of these things? You know, it probably would be something along lines like an asymptote, like this, where this might be here. This might be like right here. This would be like down here. And, you know, they're just really dropping off fast if you just have this stuff. And you're waiting for normal hydrolysis to take place. So, always drops off. Okay. Sometimes I might make the analogy of like, I heard this analogy being like what it takes to become a hockey player. All these hockey players, and if you become an NHL hockey player, well, you know, this number actually make it into college, and then of those, every 1,000,000 of those, only 1 of those actually makes it into the, you know, even to try out for a team, and of those, thousands and thousands, only 1 of those make it. It's just, to become a professional athlete means the numbers are statistically daunting. So, a couple of things about this. How do we draw cells then? Well, for this guy, maybe you would just want to draw this. I'm going to draw HX, H2X, meaning H2SO3, HX negative 1 as being HSO3 minus 1, and then X negative as being negative 2 as being SO3 minus 2. What would we draw in our picture? I'd probably just draw like a whole bunch of, if you wanted to, you really wouldn't be anything wrong with just drawing this, correct? Like that? I mean, if you want to draw a proportional diagram, you probably got to draw 100 of these before you draw one hx negative 1. Does that make sense? Maybe I'm going to draw this out, and I'm going to leave it at that. Okay? If you drew a whole bunch of them, maybe you could stretch it out, and you could draw, you know, one of these guys, because it is 1 to 100 is, you know, maybe. What if we add a slide here. What if we change this, but we look at it rather than this guy, we change it to this guy. Now what would it look like? Okay. Take a second and sketch out what you think your beaker is going to look like. I'm going to pause the video. All right, so you've had an opportunity to try it out here. Now, again, this is a good question, because what is that guy? It's strong. Okay, let's write out what reaction is going to take place here. Well, we know this guy is strong, so what's that mean? It means that we got H2SO4 goes 100%. Well, it goes 100% to, well, plus H2O yields H3O plus HSO4 minus 2, minus 1. All right? This goes 100%. It's got a Ka value that is through the roof, and we don't really know anything else about it. The next one you could look up, HSO4 minus 1 plus H2O yields H3O plus SO4 minus 2. And this Ka likely is on the factor of 10 to the negative, like, 6th, maybe 10 to the negative 8th. It's about 1,000,000 to 1,000,000,000 times smaller. So what would your picture look like here? It would be this. I'm using the same notation I used last time. Does everyone understand why that is? And I also have these guys here. Right? The last one, we never even drew out any H plus ions because they would be just as rare as the other guys are, but these guys here, even small amounts of these guys are nasty. But either way, would you draw any SO4 minus 2? Probably not. Okay. Just a quick little heads up here is that how would you actually get the Ka for this reaction? Okay. What you would do is you have the first reaction, I can write out here quickly, H2SO3 plus water yields HSO3 minus 1 plus H3O plus HSO3 minus 1 plus water yields H3O plus SO3 minus 2. This guy had a Ka value of right here. And therefore, what we do here is we take the Ka value of 1, multiply it by the other one. We know this stuff's very rare. Let's see what it comes up to. I got Ka is 1.7 e to the negative second. This is Ka1, that's for this reaction, which means 1 in 100, okay? And then Ka2 equals 6.4 e to the negative eighth. And I'm going to multiply the Ka1 times Ka2 equals Ka1, 2. Now, does this make sense? Let's multiply those together. Multiply them together, and what do you get? Again, you could estimate just by adding the exponents, but it's going to be 1.7 e to the negative second times 6.4 e to the negative eighth And you get 1.0 e to the ninth, 1.0 e to the negative ninth. And that would be the Ka value for this process, which means that overall it's, again, very little product showing up here. 1 in a billion, 1 in a trillion. Any questions? Thoughts? All right. Here we go. 20 milliliter sample of 0.1 molar H2SO3 is titrated with 0.2 molar NaOH solution. All right. How much volume is required to reach equivalence? Let's sketch the graph out. All right. So first of all, as we glance at this, you should realize we got 20 milliliters of 0.1 molar, and I'm titrating this thing with 0.2 molar NaOH. Because it's twice as concentrated, it should require half as much. So how much volume are required to this? 10 milliliters will be required. Is everyone okay with that? Well, that means it takes 10 milliliters for my reaction. All right, I have H2SO3 plus water. I'm going to use the hydrolysis equation here just to show you what's happening here. HSO3 minus 1 plus H3O plus. And then I have this guy, HSO3 minus 1 plus H2O yields SO3 minus 2 plus H3O plus. Now, I'm just showing hydrolysis. The neutralization reaction is not this. It would be H2SO3 plus OH negative yields HSO3 minus 1. So what I'm doing here with this neutralization is rolling this stuff over this stuff. And we're saying at 10 milliliters, I will have an equivalency point, where I've added enough of this stuff to completely move all of this stuff out of one house into the other one. This stuff will be down to 0. This stuff will be maxed out. And then we start going on the next one. So what's this going to look like? Okay? I know there will be equivalency. There's actually going to be two equivalencies here. One at 10 milliliters. Let's call this 10 milliliters right here. All right? And we're going to draw the next one at 20 milliliters. We'll see when. So then this stuff is going to run out. You'll have another 10 milliliters. All of this stuff gets moved over here. This is 10 milliliters. It's another 10 milliliters. What's this graph going to look like? Well, it's going to start out relatively not super acidic, okay? And it's going to start making its way up here. Well, this stuff actually has got a decent level of acidity. It's got a Ka value of 1 point. Well, we'll see here in a minute. The pKa value of this thing is pretty low. It's about 1.7. So the pKa of this thing is a negative log of this thing. It tells you the general range of pH. So if you took this guy here and you did the negative log of that guy, you get the pKa. All right? I'm going to put that over here for a second here. So the negative log of that guy here, I'm just going to take this guy and copy it. So this guy's pKa here, I put it on the next slide. I'll just do it quickly. Negative log. .7. What does that mean? It means that when the concentrations are actually equal, the pH is 1.7. That's my half equivalence point. So I'm going to start relatively low, and it's going to start creeping up here, and it's right about here. I'm going to have a equivalency point, half equivalence point, and it's going to creep up, and then it's going to have a little bit of a bump. Okay? And then this guy's pKa is right around 7. So I'll have a little higher here, and I'll have another little, well, it's going to go all the way to here. So it's going to drag out, slowly increase, and another little bit of a bump right here. And that is what my graph looks like. 2 bumps because I have a diprotic acid. And here's a more refined version of it, not too much, right there. Any questions? All right, pause here, take a moment. I'm looking for the concentration of my original acid. Doesn't matter what it is. All right, HX happens to be H2X. I want to know this guy's concentration, so I'll probably use this table here. Known, unknown, I'm being titrated against 0.1. So my moles of HX plus OH negative yields, I do have to get HX negative, but I'm knocking it out. And I want to know how many I have. Molarity, moles, liters. My known happens to be 0.1. And it took how much? This is my equivalency point down this way. How much did it take? Again, that's where the estimate comes in. Maybe this is 30, maybe say 25 milliliters. Okay? It's not nicely marked up, but that's fine. So we'll go with it. At about 25 milliliters, I reached equivalency. My first equivalency. My second one was at about 50. It's fine. How many of these do I have originally? That's what I want to find out. So it's going to be 0.025. And the moles times molarity equals molarity times volume equals moles. All right, so it's going to be 0.025 times 0.1 is 0.0025. 0.0025. That means that's how many I had these originally in the container. And 0.0025 divided by the original volume of, what do we need here? So this volume is not here. So we'll need to add that here, that part. Let's give it a volume, let's say, well, this guy's 25, let's say 50. Okay, we'll start with 50 milliliters. I'll add that. And this would be 0.05, so you should note that it should be half as concentrated, which would be 0.05. All right, let's go to the next problem here, getting towards the end. I think this is our last question here. All right, so which is the best comparison of the total number of ions in separate 1 molar solutions of compounds of the following? This is in your practice test. Well, on this problem here, what do we got? We got 3 different things. I got this guy here, which is this is really a little bit of acid, but lots of just states of matter dissolving. This guy, K2C2O4, that's oxalate. This would be a weak base, by the way. Will dissolve to produce 2 K plus ions and a C2O4 minus 2 ions. I'm going to get 3 total things breaking apart here. My total ions here is going to be 0.3 moles per liter. It's going to triple that guy. Then this one does this. KHC2O4 will dissolve, producing K plus ions and HC2O4 minus 1. This is going to 100% dissolve. 100%. So we're going to get 0.22 things here, or 0.2. This thing can then undergo hydrolysis and get a few more ions, but it's going to have a very small K value, so it's very tiny. But it might be produce a little more. And then this guy here, H2C2O4, is going to produce via hydrolysis H3O plus ions plus HC2O4 minus 1. But this Ka value is tiny. So really, we almost get like nothing. We almost get 0 on this guy. So at this point, which of these is the highest? This one's the highest by a long shot. This one's the next highest by a long shot. And this one's darn near 0. Very little. Therefore, my answer here is going to be, I believe, which is like C. Okay. So even though we have a little bit of acid, you've got some other stuff mixed into it as well.